So I'm going to begin. Welcome everybody to the Rust and Cpp Rust Cardiff group. Tonight we've got some scintillating talks. Excited is not the word that I would use. So just a quick overcap of kind of like our group and what we're kind of doing here. So we've got a couple of different places where you can kind of hook on to us and maybe even share some things within the community. So we've got Twitter, email, and we've got Discord now. We haven't recently, we haven't been particularly active on it, and that's been for a couple of reasons. But we're trying to turn a new leaf as autumn's coming. I don't think that analogy works, but yeah, so we've got Discord up now. So yeah, some objectives for this group. So what we really want to do is we want to be learning and sharing, introduce new people to our technology, C++ and Rust. We want to kind of challenge ourselves, push us out of our comfort zones. We're looking at real world solutions as well, real kind of practical knowledge and application of these technologies. And ultimately, we just want to advance all of our abilities together. So we are sponsored by Esri, who are the world's largest geoanalytical company. Incidentally, for the sake of balance, Ciara, Alex, and myself, we work for Esri. So we do have a code of conduct that we adhere to at all these meetups. And that code of conduct is based off the Rust code of conduct, which I believe is Mozilla as well. So ultimately, it's just, just be wonderful to each other, just be nice, really. And we have this Pac-Man rule for our physical meetups, but we're on the digital space now, so I don't really know how this applies. But ultimately, what it's trying to say is that when you have a conversation in a group, make sure that you always kind of leave a little bit of a space so other people can kind of hook into that conversation. I don't know how that materializes virtually, but there we go. Cool. So here are these speakers that we have for tonight. We've got Alex, who's going to be talking about face detection with OpenCV and Rust. And then afterwards, after a little break, we've got Ciara, who's going to be talking about bits and pieces with number deconstruction.
Before that, I'm just going to quickly mention something that will be coming in the future. So I'm going to very quickly share screen if that's all right, Chris, before Alex kicks off.
Yeah, oh, let me stop my share then.
So we are going to be doing some Rust book study sessions. We're going to start in 2 weeks, Thursday, the 14th of October. And they're hopefully going to be, if you know anyone who hasn't written any Rust, or if you yourself haven't written any Rust and wants to get set up, we're going to help with doing like machine setup, starting looking at the book, working through a couple of exercises, and just to kind of start the ball rolling for anyone who's new to the space. Going forwards after that, we're going to work through various chapters and kind of see how it goes. We'll basically touch base with whoever wants to come along and see how people want to shape that sessions. It might end up being people talking about projects they're working on. It might end up being just kind of going through the book exercises and discussing them. So anything we've looked at in the last few weeks, any things we weren't clear on, and just kind of learning from each other, because the book is such like a great resource. We just thought it'd be good to take advantage of that. So that's the link to the book. But if you just type in Rust Lang book or Rust book, you can find it and get started yourself, or you can wait until the session and we'll go through it then. So as I said, we're going to work through setup together, discuss chapters, and share lessons learned.
So how does one get involved with that, Ciara?
I'm glad you asked. So the event is already on Meetup. It will be, if you're subscribed, then you'll get an announcement later today to say that it's up, but you can join it now. It's there. And we have a Discord channel for kind of this meetup in general. It's not been super active, but we are going to put a channel within our Discord server for discussing going through the book and for these sessions. So please join that and say if you're interested, or just register on the Meetup, and yeah, looking forward to it.
I apologize if nobody can see Ciara's screen. That is a technical challenge that we've been trying to get over.
Oh, can you not see it?
Was there anything on there, Ciara, that is pretty valuable for us to see. Can you just put a screenshot into the chat?
Okay. Can you see now?
Yes.
There must be a keyboard shortcut for pausing your screen share. I managed to pause it somehow. But yeah, it was just what I was saying, and then the event and the Discord, but it's probably easier to search for them anyway. The Discord, if anyone, I'll put these in the chat so anyone can see them. Yeah. Over to Alex.
Oh, yeah, great. Thank you, Ciara. I should be picking up the slack there. Sorry. Yeah, right. Okay, so first of all, we've got Alex who's going to be talking about OpenCV. In your own time, Alex.
Excellent. Right, I'll just get those slides set up. 1 minute. Need more monitors. Right, can somebody just give me a wave or let me know if you can see the screen?
We got it, Alex. Thank you.
Excellent. Right, yeah, so as Ciara and Chris have helpfully said, my name is Alex, and for those of you that don't know me, I'm a software engineer at Esri. I've got a background in geographic engineering and games development software. And today I'm going to be talking about a little side project that I've been working on and off for the last few months, which I programmed in Rust, which utilizes face detection from a live webcam feed. So just a bit of background in what I actually set out to do. I've dipped my toe into Rust a few times. I've started the Rust book for my sins. I've not finished it. I've used it in a couple of game jams, and I've used it with my personal programming kata, which is a text-based game just to understand the basics of I/O. And I had another idea for a project, which I didn't have a particular need to develop it in Rust. I just wanted to make a proof of concept for a small computer game that was a bit silly, something I could work on slowly and hopefully with somewhat novel ideas. But I decided to use Rust mainly to see just how feasible it would be to run with Rust for such a project. I wasn't entirely certain what I'd end up learning, so I wasn't really looking to learn, Rust language features X, Y, or Z. I just wanted to run with a project and just see what I would pick up along the way. What I ended up learning about was not, a little bit about Rust language features that I hadn't used or picked up on before. But the bulk of what I learned was I got a fair understanding of the level of maturity of computer vision support in the Rust realm. So what I ended up deciding to do was to make a Space Invaders style game that used head tracking to move the player character left and right. And I'd done a little bit of computer vision work with Python in the past, so I had a rough idea of how such a game might work for starting. Yeah, so as I said, I've had some prior experience with computer vision. That was with OpenCV in Python. I knew the underlying library was performant and had multiple ways of doing what I was looking to do. But rather than just picking OpenCV, I wanted to get a good understanding of what the situation was like in Rust, whether there was other options available. So I did a bit of digging, and I arrived at 3 real options. The first of which is Piston, which is actually a game engine, but it had quite a bit of image processing functionality available. But when I was looking at it, it was still in development. This was quite a few months ago now. I understand they've added a few more features to it. But I actually had a roadmap, and the roadmap didn't really mention the image processing stuff much. And from what was there, didn't really look like they were going to get into serious computer vision. So I discounted that pretty quickly. The second option I saw was a crate called CV-Rust, which is a handcrafted binding to the OpenCV C++ library, but pretty quickly discovered it was incomplete, and based on the commit history, it looks like it had just been abandoned. The final thing I discovered was another crate, OpenCV-Rust, another set of bindings to the CPP library, but these were automatically generated. It is untested, so it came with lots of warnings saying, use this at your own risk. But it did offer almost full support for all OpenCV functions. And it came with the option of modular compilation. So if anyone has used OpenCV before, it's quite a big library. So being able to actually pick and choose which aspects you want to compile was a big plus. So as you might have guessed, I went for the OpenCV-Rust crate. So the first step was to get my developer environment set up, which meant I had to install OpenCV. I did it on Windows, so I used Chocolatey as my package manager, which is actually what the crate developers recommend if you're developing for Windows. For Linux, they recommended either installing directly from the repository release or to compile from source. Next, I started hitting my first hurdles. So they documented that a number of system variables need to be set in order to get the compilation to work. Fine. But I ran into a few issues in that the environment variables that I was asked to set, there were 3, if I remember rightly. There was actually a mystery one that was undocumented that I needed. And it doesn't sound like a major thing, but it actually held me up for quite a while because it wasn't very clear. I had to dig through the issue history in the repo. And it actually, what I found was that quite a lot of other users had reported similar problems. Not exactly the same one, but very similar. So it certainly seems that the build process was a bit fragile. I didn't try developing for Linux, but I saw a number of issues related to Linux dev as well. So perhaps it's the same situation with Linux. And as I was dealing with it, I couldn't help but compare the process to setting up OpenCV for Python, where you just install and set up everything via pip in one command. You don't even need to set up the library yourself. But hey ho. The final step is to install either libclang dev or LLVM, depending on your OS, as the crate depends on this for building. But that was mercifully straightforward. So once I'd had the library set up, as I mentioned, I knew that OpenCV had multiple ways of allowing me to detect faces. So I'm not going to dive too deeply into the theory behind the 3 I considered, but I'm going to just give a brief overview. So the first method that I considered was detecting facial landmarks using HOGs, which stands for histogram of oriented gradients. So the idea is that you can build up a collection of feature descriptors from an image, and that these descriptors are derived from a distribution of so-called intensity gradients within the image. An intensity gradient is a directional change in color intensity, brightness, for a neighborhood of pixels in an image. So my cursor doesn't want to stop flashing. So you can kind of see in this example image that I've stolen from the web, these little red squiggly lines are kind of laid out in a grid. So what has happened here is there's been a number of passes of small kernels or windows over the image, in which quite a lot of, if not all of the possible gradients have been determined. And then this is just a concatenation of all of them. And this makes up our feature descriptor. This collection of descriptors is then passed into some model. The reason I say some model is because it's entirely agnostic which form of model you want to use. It could be machine learned, it could be a neural net. I think citation needed on this because I read up on the subject and found that I believe support vector machines were the first model used when HOG facial detection was first conceived of. But as I say, I've lost the link to that, so citation needed on that. Anyway, so when considering how to do this, OpenCV doesn't provide the exact means to extract the facial landmarks in this way. Most people, when developing such an app, would rely on a library called dlib. It's a very common choice for working with Python, and I think C++ as well. And there are unofficial Rust libraries that bind to dlib. So it was a real option for me to do this. But I'd just come through the other side of setting up OpenCV at this point. The idea of setting up more libraries that were just binding onto other libraries didn't really appeal to me. So I decided to see what else there was. So next is a slightly more modern approach, which is called HAR feature classification. So the theory is that a predefined kernel or small matrix called a HAR feature is applied across an image to detect the likelihood of some facial feature within that image. So if I just, let's see if I can go back to slide actually. So if you remember, we passed through this image in a series of windows through the grid. A very similar process is followed here, but instead of trying to determine what the descriptor looks like as you go through, we have some predefined ones that are looking for aspects of a face that are pretty much common. And that's what a HAR feature is. It's essentially a matrix that's used to detect lines and edges where the aspect of a face would contrast between darker and lighter areas. So if you see in this example image here, we've got a black or a dark line roughly correlating to where the eyes are in this admittedly very pixelated image. This is from OpenCV's documentation, so don't blame me. But you can see that because the eyes are sunken into the face, they tend to come up darker in a grayscale image than your cheeks. So we've got this HAR feature here, which is detecting I suppose it's the eyebrows of the face. We've got another one here where again we're using the eyes to detect as the darker feature to detect the lighter feature, which in this case is the bridge of the nose. And a HAR feature classifier is just a program that is constructed to group these features in terms of priority into different stages and to apply each stage to the window. So if a stage fails, you can fail fast and just say, hey, it's not likely to detect a facial feature. But if a window passes all stages, then we know it contains some sort of facial landmark. So this approach is very fast. From the reading that I've been doing up on it, it seems like it's lots of people say it's really fast. But they all say that it only really works well for faces that are directly front facing. So again, you can kind of see it here. If it's all well and good if you've got your eyes on the if you're facing straight on, the bridge of your nose is going to be bang in the middle. If you're leaning to the side, or if your head pose is slightly off at an angle, it's not going to pick it up as easily. OpenCV provides HAR cascade facial detection via its interface, so I wouldn't have had to set up any of this. And its release files even comes with a weights file for the model used to detect faces. So I think I'd like to revisit this project and try with HAR cascade detection at some point. But ultimately, I decided to use a neural network. I'll admit to a little bit of bias for this approach. I have detected faces with neural networks in Python a few years ago, but I did genuinely consider the other options first. So for those that don't know, a neural network is a network of layers, each of which uses a series of weights to manipulate some given input data. When training a neural net, in our case for a classification, the result is determined as right or wrong, and that information is fed back into the model and used to adjust the weights at each layer. But again, we didn't have to worry about this for this. I already had a model on hand, which would have allowed me to just pass an image as an input layer and manipulate that raw data and just get some output. Is there a face and where is it? So OpenCV has a neural network module with an interface for loading in a cafe model and weights. Cafe is just a very common, very popular neural network framework. I don't know why they picked cafe in particular, but it's a good choice. And considering they provide the model for you anyway, for our purposes, it doesn't really matter too much. So this approach is very fast and doesn't require the user to be front facing. But because we don't actually determine any specific landmark descriptors, we can only really obtain a bounding box of the face as output from the model. But that's fine for our purposes. As we said, we just want to track it, where the face is going, and we just want to get a sense, just enough to move a little 2D sprite left and right. So I decided that that was good enough. So how I implemented the facial detection, it's pretty straightforward. This may look like on some of these points that I'm glossing over some of the key details, but each of these points only really correlates to one or at max two calls to the OpenCV interface. But essentially the program runs in a loop. It just starts by obtaining an image or frame from the camera. At the moment, it just grabs an image from the first registered camera device, but that would be trivial to extend. The image is then pre-processed into the size expected by the neural net and converted into a blob type, which is then passed into the neural net. We trigger a forward pass of the model, meaning the image data is then told to traverse through all the layers. And then we just need to get our output, which comes in the form of a matrix, which contains quite a few other interesting little tidbits that you can experiment with. But all we needed to get was the bounding box of the image supposedly containing the face. And those positions come back normalized. So we just need to multiply those by the width and height of the original image to get a bounding box that sits covering a face within the original frame. And I've just said that bit. My notes have repeated the same thing twice. So how did I get on? Well, it works. I was able to write a face detection program with Rust. It's pretty performant. I've got a few video clips that I'll be showing at the end, so you can see for yourself that it works quite well. Many of the crates functions. Oh, sorry. So what did I? Why else? What else was a success beyond how it performed? Well, I found it quite nice that many of the crates functions returned values wrapped in Rust's result type. It prompted me to write a lot of matches, which resulted in code that I guess ended up looking a bit like a try-catch block. But it's the fact that Rust's type system actually prompted me to do this rather than, say, with C++, just getting a raw pointer back and thinking, oh, yes, I'll just handle this. Because it was deliberately wrapped up in a type, I was forced to deal with it in some way, either by explicitly unwrapping it or the nicer approach to actually write my match functions and implement some error handling, which I found that really nice. I also found that there was quite a lot of documentation online, which of course it is. It's quite a big library, and there was auto-generated documentation for Rust, which was nice to have. But because the functions had a pretty much one-to-one mapping with the C++ implementation, anything that I couldn't glean from the auto-generated documentation, I could just go and get the existing doc, and most of the time it worked fine. So overall, I'd say it's extremely feasible to port an OpenCV-based application from Python or C++ to Rust. However, so it wasn't all fun and games. So in addition to the difficulties I had setting up the crate, I also found a few problems during development as well. I slightly misled you earlier when I said that the interface was pretty much consistent across the Rust and C++ and Python versions. That's not entirely true. I was hit with a couple of stumbling blocks where the expected arguments, where the arguments of a function weren't treated in quite the same way. So for one particular example, when you're requesting your output layers from the neural net, if you're using the C++ or Python interface, passing an empty string means that you're requesting to get back all the output layers. In Rust, for some reason, it meant none. I wasn't sure why that was, but it tripped me up for ages because There was nothing in the Rust documentation about it. And of course, there wasn't anything about it in the C++ doc. In fact, that actually said if you pass in an empty string, you'll get all of them back. So it was a bit confusing. Additionally, OpenCV's interface has specific types for input and output to and from functions, which the auto-generated bindings for Rust made overly complicated when converting these types to traits by obscuring the underlying type. So again, another concrete example, there's a type called output vector, which was converted into a trait. However, the OpenCV functions returned concrete types of that output vector. Rust was just returning output vector. And that meant it got a bit confusing when I was dealing with vectors of vectors, because they both had the output vector trait. So I wasn't entirely sure what I was supposed to be getting back, and how it was a bit confusing to figure out how many dimensions I was working with in the data source. I also found that the end result was a program that was very coupled to the design of the neural network, which ended up meaning that I had to do some necessary casting of output data, and I ended up with hard-coded indices for extracting data from the result matrix. Those aren't necessarily failings of Rust, because it's more about the choice of implementation that I chose. However, I did like how the Rust syntax makes this really easy to see. So again, I went back and compared to the Python program that I had written a few years ago, which did something similar. And it was amazing to just see that the Python program had the exact same problems, but Rust syntax made it really clear that I was running into this coupling between the data and the model. So next, I decided to integrate it into the game. So I ended up packaging the face detection code into a crate called ftrack, which you can download now from Cargo. I have lost my notes for this slide, but I mostly decided to create the ftrack crate because I'd never created a crate before, and that was the whole point of this project, was to try new Rust stuff. So I did that. I won't go into details about the process because it's well documented online, and I believe Chris has given a talk about that in the past, but it really is easy. My first time doing it took me about 5 minutes, and most of that was signing up for an account with crates.io. So it really was a breeze. So the way ftrack works is it just runs, when you kick it off, it just runs itself in a separate thread, or the game runs ftrack in a separate thread. And the game retrieves bounding box data from the ftrack thread via channels. So channels are like a nice directional way of sending data from one thread to another in Rust, and you can find that in chapter 16.2 if you want, if you've not come across it before. And essentially, all the game does is take the bounding box, map it to the game's coordinate system, which it just needs to do by just with a simple scaling routine, which is hard coded at the moment again. But we just scale it so that the bounding box, which is in the webcam space, just increase the scale the width and height so that it matches into the game window. And then we just set the player's X position to be the X position of the scaled bounding box center. So just reminder, we're only moving him left and right, so we only need the X coordinate. And all my notes have come back right at the end of the slide. Right, so let's enough jibber jabber from me. Why don't we actually look at it running? So if you just give me one moment. So I've got two videos for you. The first of which is me just running ftrack's debug program, which comes in the source. And it's decided to open on the other window and not let me transfer. Sorry, technical difficulties. No, that's wrong button. There we go. So yes, this is ftrack running with its debug program. So it's just just taking the image frame and just applying a bounding box before printing that frame out to the screen. So you can see as I twist my head around and try all sorts of different poses, move around, it still keeps continuous track of my face. I'm not sure what I'm doing here. Oh yes, I'm trying to put my head into more awkward poses to just see where it sort of gives up. And you can see that's sort of 90 degrees to the camera. In fact, actually, it's still picking it up a little bit there. So the model is quite good, and you can see it's keeping track with my face quite well. So it's pretty quick. The next image is going to be the actual game running. So just before anyone asks, I also decided to use I guess what you could call a unique form of control for the gun for the game. I was going to talk about it in this talk briefly, but it was really easy to set up. It was just install a crate. OpenCV, what I've learned is that that's not so mature in the Rust world, although there is quite a lot of functionality. When it comes to 21-year-old Nintendo controllers, there's multiple crates that you could possibly use, all set up and ready to go. So you can see the character sort of moves left and right. This second monitor is a bit big, so that's why I've come back here. So as my face moves left and right, character does so too. I haven't got much room with that stupid cabinet, so I ended up going further back and doing all kinds of crazy stuff to try and get more movement out of my physical moves. If I stood up, maybe that would be a bit better. And I think I'm just going to let it end in a minute. Yeah, there we go. So thanks for listening, everybody. I'm going to upload these slightly updated slides to my repo. You can find me on GitHub as Payne325. You'll also find references and links to the various articles that I read while I was working on this as well, and for the borrowed images from this presentation as well. So with that, are there any questions?
Yeah, thank you very much for that, Alex. If you've got any questions for Alex, just you can either ask directly or you can write it down into the chat, and I'll read them out for him.
So was the shooting control controlled by volume, your microphone?
No, no, it was controlled by these. So I'll just open these up. It's sort of like a precursor to a Guitar Hero controller. So in about,
all right,
in the early 2000s, it was it's a bongo drum for a Nintendo game called Donkey Konga, and
okay,
it's like a rhythm thing, and you just slam on the button and it detects a shot.
I thought it's a classical bongo, and then you just collect sound of it and feel.
Oh no, it's no, it's like a Guitar Hero toy thing.
Yeah, so I misunderstood it. I'm not in the world of Nintendo.
No, that's fine.
Not many people in the world of obscure interface devices, that's for sure.
Well, that's what I thought, but I found more than 2 Rust crates that supported adapters for. So there's an intermediary device here, which is a USB to GameCube adaptable crates out there that handle polling this device via Rust. So once I installed one of those crates, just pick the newest, nicest one, getting that to work was really trivial.
To be honest, it doesn't surprise me that there's crossover between the Nintendo esoteric random bongo drum community and Rust programmers.
I got to say, I was a little surprised, but maybe that's I just haven't spent enough time on the internet.
Hi, Alex. Great talk. Thanks for that. that the F-Track demo you showed just before your video game demo,
yeah,
it was extremely scarily effective at tracking your face. How much training or setup did it require before it was able to match your face so precisely?
So I don't know exactly, because the model actually used to come with the OpenCV source. I don't know if it still is. That's why I put used to be. But when you look at tutorials for this kind of thing online, it's widely shared. My understanding, it's using a training set called VGG16, or it builds on that, which is quite a large data set. We're talking like tens of thousands of images. I couldn't say for certain how long it would take to train that model, but it's widely available online, so I didn't have to deal with that.
But it did, so it came pre-trained. You didn't have to train it yourself to recognize you.
Correct.
That's good.
From you-
Completely different. On the software engineering side, you mentioned that you'd had fun getting used to dealing with the result return types for which sort of handled lower level error trapping. Did you find that meant everywhere you trapped it, you ended up returning a result from that function? So you ended up with a sort of cascade of result objects all the way up to whatever the control level of your program was?
I wouldn't say it was a cascade, because it was there weren't results wrapped within results, if you catch my drift. Generally speaking, it's pretty good. So I was either checking, if it was okay, then we'd carry on with the program execution. An error would have just cancelled F-Track entirely, because I say it's just a proof of concept. I didn't really find with normal operation that happened very often. The only times I could really remember an error message occurring was if I'd accidentally kicked the webcam out of its USB slot or something. But it's generally just yeah. If it fails, we fail hard, and if we succeed, we just carry on. There's no real cascade of errors going on.
No problem, just curious. Thanks.
You've got a user request here from Ewan who suggests, can you please do this again with a motor racing game, Alex?
In what sense? So the controlling the car? Well, I suppose, of course, it's controlling the car. I'm getting too obsessed with it. I'm going to put those away because it's making me come up with stupid ideas. It's the worst thing I ever got. Love it. Yeah, so I guess you could have something like one of those old school racing games where you're moving forward, but your camera never really leaves the bottom section of the screen. Is that what you're kind of imagining, Ewan?
Motorbikes, he's suggesting. So you
Motorbike.
can lean into the corners, I imagine.
That would work better, actually, because I was tending to do this a bit more. Well, I'll have to write that down somewhere. But if don't wait for me. If you feel like it, I encourage you to use F-Track and make a similar game, follow in my footsteps.
Maybe or maybe not, because what chaos and what insanity lies down those bongos, maybe it's not for the best.
That's up to each to their own, I suppose.
Do you have any more questions for Alex in his talk?
So I have a question about you did mention that you wrote something similar in Python some time ago. Sorry for the noise.
That's okay.
So can you compare how did it work for you in Python and in Rust?
So it's I don't know how fair of a comparison it is, because I was sort of learning Rust along the way, which I wasn't doing so much with Python. I did find that getting to grips with the actual setup of the library and things was where I lost most of my time. As I said, with Python, it is really just pip install OpenCV, and you get the Python bindings, you get the library installed for you, all just sort of handled behind the scenes. With this, there's lots of version tracking, so you not only have to install the cargo crate, sorry, the crate via cargo, but you also have to make sure you install the right version for the version of OpenCV that you've installed. And if you get a mismatch between those, the compilation is not clear. In fact, I think I wasted quite a bit of time at one point trying to replicate this on another machine, where I found I'd installed a slightly newer version of OpenCV, and then got no hint as to why my particular version of the game wasn't running. I just needed to update the OpenCV crate. When it came to the actual implementation, again, it's plus really, because it's closer to that interface.
Have we? I think we lost Alex.
The Python phase.
Oh, he's
no.
back. Or was it just me?
It's my internet connection is unstable apparently. How much of that did you just hear? Or am I still gone?
No, we got most of it. It was only for a couple of seconds, but I don't know if it was critical seconds that were required.
So just where was I? Yes, so the interface is for the Rust bindings are closer to the C++ ones. Python does try and abstract away a few things to make it easier. I guess because that's just the nature of the people working with it with Python. They need it a bit more simple for their use cases. But as far as the implementation goes, it was relatively, I'd say, equal in terms of effort. But again, this is bearing in mind a number of factors, such as I'm still learning Rust. I've got a bit of experience with the theory already. But I think I think it's fair to say that it's comparable to developing for C++.
Great, thank you very much, Alex. We should probably move on because we've, as you would say, jibber-jabbering too long on this. But if there are any other further questions, drop them in the chat and we'll kind of get onto them later. But up next, Ciara is going to be talking about what she's going to be talking about. But shall we take just a 5-minute comfort break and we'll come back? How does people feel about that?
Sounds good.
Sounds good. Thank you, Alex. That was great.
Thank you for having me.
I have to buy some bongo drums to play the game.
Oh, you can't get them for love nor money now.
See you in a mo.
So it's easy. Fork the project and work with the microphone, right? It's only for shooting.
Oh, this is cruel. Because I know you're joking, but but the temptation is there, isn't it?
Yeah, people might fork it, or you might do it.
Yeah, I could just scream bang down the microphone and see what happens.
That's great.
And then you have to have speech detection, so actually detect the word bang.
But no, even like hitting on a table or something, right? And then detecting the short duration bangs.
Well, so this. Oh, I've just moved it away now. So those bongos actually have a clap sensor built in. So at one point I considered just doing this to fire.
Yeah.
But I don't know. It seems to be a pretty common problem. Nobody can really find a way to get that to work when you go through various USB adapters. It might be that there's just a secret extra pin that's not being read or something. But yeah, I looked into it, and it's not like it's just a Rust problem. It's a problem for anything that reads those devices, which is a shame. But yeah, I'd definitely like to consider using the mic at some point.
Yeah, it's a great job you did that, really.
Thank you very much. My throat is so dry after that. That's a good question, Tim. No, or at least not with F-Track. That's a good point. My understanding is that the data set that model was trained with is large enough that it should cover a wide variety of faces, including not just with various skin tones, but also with different types of hair, hats, glasses. That was a big one. I've got quite large, obnoxious glasses. So I wasn't sure if it would detect a face with those, because you can see like the dark rims actually might put off some detection if you were going to use some of the more classical methods that I mentioned before. So I believe it should work, but I don't know. I'll have to try out. You're welcome. Thanks very much. I'm just gonna get a glass of water because my throat's a bit dry. I'll be back shortly.
And he was dancing great on that F-track testing.
Yeah, that video is amazing.
Good disco moves.
I like the choice to try and lean over the table rather than change the conversion between the center coordinates. Scaling factor.
We also appreciated your moves. You must have exercised that on the disc or something before.
So at one point I was planning to do it live for this talk, and I was rehearsing it last week. And this, I referred to it earlier as the stupid cabinet. I hit my knee really hard. So yeah, I'll find a bigger space.
Yeah, no swearing while being recorded, right?
Yep, exactly.
That will actually be broken by my talk, so can't be helped. Not my choice.
Oh, well, I can't be the first one. If you go first, then it's fine.
Okay, by my reckoning, I believe that was exactly 5 minutes. Right. Okay. Well, Ciara, would you like to introduce your talk?
Yes, I would. So I think, as mentioned, I'm Ciara, and yeah. So this year, I'm just giving some context of where the talk came about. This year, Microsoft released the tool Copilot, which is the AI-based programming companion that auto-generates repetitive code, and it's had some drama associated with it. But someone showed that you can get it to spit out a block of code, which is this block of code, the fast inverse square root code, which some of you might recognize because I think it's quite famous, but this was the first time I'd come across it from Quake 3, apparently, although the original author is a hotly debated topic by people who are interested. And when I saw this, I was quite interested because it's promising to do this operation in a slightly less accurate but potentially faster way. It's doing an inverse square root, which is commonly used in lots of games. And it's doing this using the knowledge of how floats are stored, a couple of bitwise operations, and an iteration of Newton-Raphson. So I wanted to discuss this code from the bottom up, starting with Newton-Raphson, and then building up the bitwise operations and see why they're being used. And try and answer the question of whether or not this code is even relevant today. And I promise, hopefully, well, I won't promise, but there's a very high chance that this constant, which has the expletive on the line, will make sense by the end of the talk, hopefully. So what is this function trying to do? Well, as I said, it's doing 1 over the square root of the input. And if we're bothering to write a special function, then there's kind of an implicit assumption that square roots or division are slow. And we're going to question that assumption a bit later, but let's stick with it for now. Our aim then is to write a function which does an inverse square root with neither a division nor a square root. And the Quake code does this by rephrasing it as a root finding problem. A root finding problem is one where we want to find x for which there is some function which when valued to 0 is what we want. So we're trying to find the zeros in the function. Since the thing we're trying to find is 1 over the square root, if we say x is 1 over the square root of the input, then we just need to rearrange it so we've got 0 on one side, which is just x squared equals 1 over the input, or 0 equals 1 over x squared minus the input. So now we have an equation that we want to find the root of. So when it's 0, that gives us what we want. And there are a fair few numerical methods out there for finding roots, and the Quake code uses Newton-Raphson, which is, I'd say, probably the most commonly known about one. As mentioned, in Newton-Raphson, we're looking for the root, which is where our curve crosses the x-axis, where it goes to 0. The premise of Newton-Raphson is that you guess an initial solution, you use the tangent line to the curve at this point to get a new guess from where the tangent crosses the x-axis. And we can then approach the true root with successive iterations, getting closer and closer every time. There are a couple of caveats, but generally it's pretty reliable. So if we imagine that 0.6 was our initial guess and zoom in a bit, then provided our function is differentiable, we can find the gradient of the tangent by differentiating our function. And then we can just use that to plug it into this formula by calculating those two distances to give us our new estimate, which is this second dot marked on the graph. Which in our case, it looks like f of x is 1 over x squared minus the input. Rearrange that to make it easier, minus 2x minus 3. We then just plug that into our formula, and we have something we can work with. So yeah, so x1, because we're doing this iteratively, or at least we could do it iteratively, that's why I've written it with subscript 1. So our x1 is x0 minus x0 to the minus 2 minus input over minus 2x0 to minus 3. So x0 there is our initial guess, and then this is just a Newton-Raphson iteration to give us a second guess, which is just what this graph was showing here and there. And once we've got this, it's actually directly equivalent to our Quake Newton-Raphson iteration. We've just done a slight bit of rearranging. You know, they've put a constant in for half the input. They've used y instead of x0 as an initial guess, but everything else is identical. And this has no division, only multiplication, and it can be proved that if you repeat Newton-Raphson iterations, it has quadratic convergence. So it's plausibly a start. But to use this method, as I mentioned, you need a starting guess, and the quality of this starting guess will heavily impact how long it's going to take you to get to a halfway decent answer. And all of the Quake code prior to this, the meat of the actual method, which is basically just that one line, is for doing exactly that. So trying to get a good initial estimate that we then improve on with a single Newton-Raphson iteration. So now we need to get into the meat of the code, but to do that, we're going to have to look initially at some bitwise operations. The main bitwise operations available in our bag of tools are the AND operator, which takes two operands of the same bit length, performs an AND on each bit, and then the result will have 1 in that position if they both have 1s, and if not, it will be 0. The OR operator, which, as the name suggests, takes two operators and does an logical OR on each bit. So if either of them or both of them are 1, then it will return 1. The XOR, or exclusive OR operator, which means that if they're both 1, it will just return 0. But if one of them is 1, it will return 1. Both are 0, return 0. The NOT operator, which just flips all the bits. And then the left shift and the right shift. I thought I was going to have a bit more time to talk about left shift and right shift because there are some slight subtleties to it, but I'll see if I have time. But yeah, since we're using the shift operator, we're going to start just by looking at the simplest example, which is right shift. If we right shift on an unsigned integer, this is just dividing by 2. The end result will end up halving our number, and this is pretty useful, as we will see in a bit. In reality, dividing by 2 will just do this for you, but it's nice to have anyway. It's nice option. So back to the Quake code. Those were the bit shift we talked about there was on integers, but the original code in Quake is talking about floats. So we're going to need to look at their structure. Like the code, we're going to use IEEE 754 floats, which is just a standard format, and we're going to briefly lay the groundwork because it's useful. IEEE floats are basically just scientific notation in base 2. So while in scientific notation, you might write 223 as 2.23 times 10 to the 2 and 0.03 as 3 times 10 to the minus 2. In base 2, you would just be doing the equivalent, but for 2. So here, 12 is represented as 1.5 times 2 to the 3, or 1.5 times 8. And 0.875 is 1.75 times 2 to the minus 1, or a half. For powers of 10, you can see this, actually there's a typo on that slide. I've written 2.233. That should be 3.0. So yeah, but you can see from those examples that that leading digit in base 10 is important. You need to know whether it's 123 or 223. But for base 2, that 1 doesn't matter because it's always going to be 1. If it wasn't a 1, everything would just shift along again. And you would have a larger power on your exponent instead. So we're going to need to bear that in mind when we're looking at our representation. When we want to store this, this is the way it's useful to think about the information that we need from scientific notation. So we need the sign, telling you whether it's positive or negative. We need this mantissa because we know that the 1 isn't important. It's always going to have a 1 at the start, but those decimal places like the 1.5 in 12, the 0.5 is important. And we're going to need an exponent, which is going to tell us our power of 2. And floats typically use this for storage. So they're storing the sign, which is whether it's positive or negative, the exponent, typically 8 bits, and the fraction or the mantissa bits, of which there are 23. So I just want to go through a couple of examples because crucially that power can be negative. And if we want that power to be negative, then we're going to need to represent negative powers in our exponent bits. The way that's typically done is when none of the exponent bits are set and none of the fractions set, then it's 0, because 0 is a special case. You can't get to that from a power of 2. When you have just one of the bits set, the rightmost bit, then you're going to have the lowest possible exponent, which is minus 126. If you have the first 7 bits, then you have 0. If you have the leftmost bit, then you have 1, 2 to the 1. And if you have all except the first bit set, then you have 127. There's 2 other special cases, which are when the exponent bits are all set, which are used to represent infinity and not a number, with infinity just being when the mantissa bits are all set to 0, and nan being anything in the fractional mantissa bits. And my understanding of why, the mantissa bits, when they have values in nan, are kind of wasted is that you can, I think some people have put information in there secretly to say how you got to nan. So they're kind of useful to have hanging around, but also it makes it simpler as well, not to have some special behavior there. So it becomes convenient at this point, if you're still with me, to introduce some notation to differentiate between the bits interpreted as integers and the values they're trying to represent. So in the example of 2 to the 3, when we're representing the number 3, because we need to represent negative numbers in our exponent, we need to have added on this 127, so it takes us up to 130. And for the mantissa, we're representing 0.5, but if you look at the bits that we're actually using, it looks like 2 to the 22, because the smallest bit is on the right-hand side and the largest bit's on the left. So it's 2 to the 22 divided by 2 to the 23, and that's how we get our fraction out. The letters that I'm using here, I've chosen to stay in sync with an article that I found online. Actually, I didn't find online, my friend found online, by Christian Plesner Hansen, who in turn used this notation based on a 2005 paper by Chris McHenry, which I could not find anywhere online. So if anyone can find that, then please let me know. But yes, we're using small e to represent the actual exponent, which is 3 in this case. Small m to represent the mantissa, which is 0.5, and then big E for the exponent as an integer, and big M for the mantissa bits as an integer. Our bias, because we're using float 32, is 127, and the smallest fractional part is 2 to the 23, which means that if we want to get just between our values, we can straightforwardly say that the exponent is the exponent bits minus the bias, where the bias is 127, and our mantissa is the mantissa bits represented as an integer divided by the smallest unit, which is the largest unit, the size, the magnitude of 2 to the 23. And that means that our value at the end comes out as 1 plus the mantissa times 2 to the e, or equivalently with substituted in large E and large M, sorry, and B. And we can also go back the other way. So if we take our example of 12, we deconstructed 32 and the first sign bits and the 8-bit exponent and the 23-bit fractional part on mantissa becoming, so we've got 1.5 times 2 to the 3, then end up with 130, and our 0.5 multiplied by 2 to the 23 to get our 2 to the 22 mantissa bits. So now that we've broken down what a float is, we can start seeing what this block of code is, but I just want to do one final bit of bookkeeping, which is introducing the idea of the whole float interpreted as an integer. We can deconstruct this into the floating point exponent bits and mantissa bits just straightforwardly by adding them. So you have the mantissa, and then you have the exponent times L, which is, remember, was 2 to the 23, and that's just so you're shifting the exponent bits back up to their correct position. Assuming everything's positive, but in this case, that's fair enough because we're doing 1 over the square root of something, and assuming we don't want to get into complex numbers, it's pretty fair to assume it's positive and non-zero. So let's go back to the code, starting with this first line. C++ doesn't allow direct bitwise operations on a float. So this line here is just to reinterpret those float bits as a long, which allows us to operate on them directly. And it does this by taking the address, casting it to a pointer of a long in their case, or an integer, which I think was what their long was back then, 32 bits, and then dereferencing that integer pointer to get us our integer, which is just the bits of the float. And now we can manipulate the bits. How can we get an initial guess for the square root of them? So this is where this clever bit of trickery comes in. So I've already mentioned that assumption that we're making, but we still need to know where this actually came from. So it's tempting at this point to get drawn in to the bit shift operator, but actually we're going to sidestep that for now. We're going to go back to the original equation and instead take some logarithms, because we're dealing with exponents in our float representation, so it becomes convenient to take logs. So if we take a log of the left-hand side and of the right-hand side, then we end up with something like this. So we have log to the base 2 of the result. We have minus a half log to the base 2 of the input. We substitute in our result and our input represented as base 2 scientific notation. And we end up with log to the base 2 of 1 plus m result. And we've pulled out the 2 to the e result and 2 to the e input because we're just using log rules there. They're multiplied there, which means they become addition. And log to the base 2 of 2 to the power e result or 2 to the power e input is just e result and e input. And my brackets are wrong on the second equation there, so don't copy this directly. I'll correct that before I put them anywhere. That bracket should not be there. So we still have a couple of logs hanging around even with this representation. But fortunately, we now actually know something about the values inside, which turns out to be very useful, which is that the mantissa is always between 0 and 1. We kind of showed that earlier with our scientific notation, that we know that mantissa is small. And if we know that mantissa is small, we can now make an approximation, which is going to turn out to be very useful. We have a look at the graph, and we just look at the values of log of 1 plus x between 0 and 1. And you start to see that it has crossing point at 0, 0 and 1, 1. And we can approximate this to a straight line. It's an assumption, but it is a useful assumption, so we're going to make it. And we're going to offset that line. Instead of just doing a line straight through the origin connecting those 2 points, we're going to offset it slightly up by some value sigma, and that's just to get it so it's closer to this log base 2 of 1 plus m for more values. And it's actually that choice of sigma that is going to become prudent in finding out where that number came from. So we can now get rid of the logs because we're estimating our graph as a straight line instead. And we're going to substitute it in so that we can then expand it out. So far, we've written it in terms of the real mantissa and the exponent. But since we have the float format, we're going to substitute in the exponent and the mantissa bits instead, which we looked at earlier. Now our exponent is offset by 127 and our mantissa is scaled by 2 to the 23. And we can get rid of those 2 to the 23 fractions by just multiplying them out and then move all our constants like 127 and sigma all to one side. And by doing that, you can now spot the thing we looked at earlier, which is that if you have m plus le, that is just the integer representation of the float. So if we go back to this slide, you can see it's just straightforwardly popped out there just from that rearranging. And now we've got I result and we've got I input, which are just the values reinterpreted. And it's this bit in the middle, that 3/2 times 2 to the 23, open brackets, 127 minus sigma, that is actually our WTF code that came up earlier, just pops right out. If you put in a value of sigma of 0.0450465, which is just taken, that's just an approximate value that someone chose at some point to approximate this line here, then the value is just there. And you don't have to choose that value of sigma. You could choose a different one if you wanted. And there's discussion online over what would be the ideal value, because rather than it being the line that would best approximate the log of 1 plus x graph, it actually isn't exactly that to get the best values for this particular case, because we're doing that Newton-Raphson iteration later, and because there's floating bit weirdness where you end up with values not being exact. So the main way that I can see that this value gets arrived at is through trial and error, and it works pretty well. And then the bit shift there is just halving the integer, because as we mentioned earlier, if you bit shift an integer to the right, you're just halving it. So now we can update that comment to, gosh, this makes absolutely perfect sense. I am not at all scared by that number anymore. And yeah, does it work? Well, I had a look and it definitely does work. So this graph here is showing the standard library code against the Quake code, and it does actually stack up just fine. But the whole reason for this slightly confusing block of code was that it was supposed to be fast. So that's the thing that, before we reach down and copy this code into all of our code bases, that you want to have a look at. And I found that it depends what you're comparing against, because it is slightly faster than the standard library when your floating point model is set to precise. I'm testing on MSVC here. But if you set it to fast, which presumably would be what you want since you're not doing it as accurately, then it's actually, this fast code is 3 times slower than the standard code. So probably shouldn't be using it in this case. But there's also the question of, should we ever use it? Well, in this particular square root case, as we said, probably not, because it's very well optimized. My understanding of how it's optimized, I think there's actually an assembly instruction that does this, and the way it does it is it has a lookup table for that initial guess, and still does some equivalent of root finding on that exact problem. So it's not hugely different, but obviously that's very well optimized. But what's cool about this method, though, is that it's actually not very tightly coupled to the exact power, and we can repeat the deviation and get something which works for any power. It doesn't necessarily make sense to do it for powers greater than 1, I think, just because you could just multiply them out and then just reduce it down to just between 1 and -1 and 1. But you end up basically, if you run through that derivation again, just 1 minus the power times L, which was our 2 to the 23, our B, which was 127. And again, the L and B could change depending on whether it's a float or a double. But you can then use this for a different power. So for example, if you wanted to raise something to the 5th, which I did have a whirl at, then you can just generate a new constant, and that also works. And I did some timings on it, and came out as about 4 times faster, even using the fast math on MSVC than using standard power. Obviously, it's going to be less accurate not least because you don't have the Newton-Raphson anymore. You probably could use some equivalent of a Newton-Raphson, but you're not going to end up with that nice bit shift because you're not going to get, you're not going to get it popping out quite so. Sorry, not the bit shift. You're not going to get the differentiation, getting rid of all of the division, for example. You're still going to end up with some division and probably another power. And if you could then approximate that, but I didn't do that. But there might be some room for improvement. But even so, it's not actually a bad a bad fit. I just did a few test points, but it seemed pretty good if you don't care too much about super exact values. So conclusions. Well, I'd say the main conclusion is that floating point representations are not only cool and fun, but they allow you to take advantage of that storage to do certain operations much faster. And the log rules and small value approximations that people learn at school are useful. And in case anyone ever doubted it, I'm sure they didn't. But yeah, it was cool seeing them like pop up in this context. And yeah, I'd say the big caveat still holds though. Just because it says it's fast doesn't mean that it is, and there's usually a cost, which is accuracy or speed. Yeah, that takes me to the end. I had a couple of extra slides just on some other ones, but I think, oh yeah, useful links. So I'll put this in the notes. That 2012 blog post was, I say, by far the best description of the ones I read in terms of clarity. And that was based on the 2007 paper that I mentioned, which I cannot find. If anyone has it, then please send it my way. And a couple of other kind of papers. If you just want to look at floats, I think the float converter as an online one that just shows the bits can be really useful for when you're first getting familiar with the format and seeing if there's anything useful you can do with it, just to play around with it. And there is a whole list of bit twiddling tricks, which I am not going to have time to cover, I don't think, looking at the time. But I ended up taking up most of my time talking about this one, so hopefully that's enough for now. And yeah, thank you for listening.
Great, thank you very much, Ciara. That was amazing, absolutely amazing. So, anybody got any questions for Ciara with her talk? Again, you can write it down as a message, and I will read it out to her.
You have funny interests, Ciara, hobbies. I think so. This code might have some problems with the portability, right? Because I don't think the IEEE 745 or whatever representation of the floats was in the C++ standard. It might have changed recently, but for the previous standards, it wasn't necessarily the case, if I recall correctly. But anyway, that's just picking up on it, right?
Yeah, that could well be true. I didn't actually check. They seem pretty widely used, so yeah, I guess if you're using it cross-platform, then definitely be careful.
Also, it was casted to long, the float itself, and it's not given that the long is gonna be 32 bit like the float is, right? So it depends on the architecture, I think.
Yeah. So when I did the code, I switched it to int 32_t. So I would never use this code that they put in. I would say don't use that exactly, and also don't use it for that particular use case. Yeah. So when I did the performance testing, I switched all the types to to the ones that made
that
most
was
sense.
my suggestion as well.
Yeah, for that exact reason. It's yeah, the long is normally not 32 bits anymore. Definitely. I think it actually still might work. I think it would still work for a long, but there's just no need to use a long because you just end up with dead space, which is actually fine.
Not necessarily, because then.
Oh, of course, you could cut into a float backwards. Yeah, you're right. Not necessarily. I think it might work, but it might not. They probably don't do it.
Yeah. Also, like you did mention that this bit shifting by one. I think it's recently by any compiler optimized, so division by 2 is optimized by the bit shifting.
Yeah.
I think Matt Goldbolt was mentioning that on recursive recently. He was, yeah.
That doesn't surprise me. I tried to kind of stick to the code and try and explain how the code worked, but yeah, I wouldn't. You definitely wouldn't necessarily want to write that way.
It's just
no,
mentioning.
It's worth mentioning, definitely. Yeah, it's convenient, and also it is worth mentioning because one thing I was planning to talk about but then didn't end up doing was the fact that if you, rather than the right bit shift, if you look at the left bit shift on signed integers, sorry, do I mean that? Even the right bit shift actually. So the right bit shift on signed integers doesn't do a plain dumb bit shift. It does actually half the value still, even though that first bit is a 1 and it's represented using the 2's complement representation, which means I should have added in slides for this, just so I was going to bring it up anyway. So basically, rather than representing like -3 as just the bits for 3, but with the sign bit at the start set, in unsigned integers, they represent it with the 2's complement representation, so that then when you add them together, so if you add -3 and 3, you just end up cascading all the 1s and you end up with 0, which is what you're supposed to get. But then the downside to this is then if you do a right bit shift, you're going to end up shifting potentially that the 1 from the sign bit, it might get shifted in, and then you'll end up with a 0 at the start, which flips the sign of your value. And then if you carry on shifting again, you're going to shift that 0 into the complement bit, and you just end up with weird behavior. So the right shift actually moves the sign bit into the neighboring positions, so it doesn't pad with zeros like how it does for every other thing. And it's described as the logical bit shift versus the arithmetic bit shift. And so for unsigned integers, you're going to get the arithmetic bit shift to save you from yourself. But it kind of highlights the fact that you kind of need to be a bit careful when you're doing these things and check that they're doing what you think they're doing.
I was hit by that problem some time ago.
Oh, really?
A long time ago.
Yeah. And then yeah, and then I also came across rotation, like bit shifts, of which there is, I was going to potentially say that there isn't a way to access the assembly instruction to do that from C++, but there actually is as of C++ 20. It's like rotate left, ROTL, to rotate the bits left or rotate the bits right, which I thought was, I don't know who's using it, possibly someone with cryptography, but it's interesting to know anyway, the fun things you find along the way. Yeah.
Thank you. Great talk, a fantastic explanation of how all that worked. Do you know, were there any limits on the range of the floats that the users could put into it? I could imagine in a game setting like Quake that they had a specific range of floats that they were going to want inverse square roots of, and that there would be limitations on it.
Couldn't see anything from the derivation that would mean that it would be limited. Because it doesn't matter about the kind of the range of floats available and the range of integers available to you when you're just casting the bits. And then in terms of the operations you're doing, the integer addition and subtraction will be fine. And your value is getting smaller when you do the 1 over the square root. So it should be okay. If you're raising to the power, because it works for positive powers as well. If you're raising it, obviously you could potentially get into issues when you end up hitting the limit of your float. But that's true even if you do it with the standard library method. So I
couldn't see anything in your derivation that would limit it. But the reason I mentioned is that there's a similar trick where you use a magic number and a bit of bit twiddling to try and extract the integer part out of your float, and to try and turn your float into an int, which is much faster than casting it. Because if you cast it to an int, then it has to completely reset the numerical pipeline, and everything grinds to a halt. So you can use bit twiddling to try and turn your float, or to get the integer part out, but that has built-in assumptions about the range that you're interested in. And you also get some slightly weird aliasing where the values alternate whether they're rounding up or down. So, particularly on the sort of maps we were doing, you were basically getting stripes across the page as we were trying to turn our coordinates into their integer equivalents. So similar tricks can certainly have weird side effects if you're not careful, but it looked like, the one you were using actually gives you a pretty smooth calculation.
Yeah, it works surprisingly well. I think in any case where you're trying to actually use, a sensible integer based on the float value, then I can definitely see that you would run into the issues. But for this one, other than the 0 and the negative cases, so if you put in 0 or negative values, those definitely won't work. But anything else other than inaccuracies, it should be solid one would hope. If you put in 0, you will get nonsensical results. And actually, when I was generating my test data, I forgot about that. So when I was creating the graphs, I was like, where did this point come from? And then I was like, you created random numbers and you put the 0 in there. So don't do that. But yeah, it's pretty reliable otherwise. Yeah, it seems to be anyway.
Nice, thanks.
Great. Do we have any more questions for Ciara? No, I think.
Just one more.
Okay.
Dare I ask if you've tried it in Rust, Ciara?
No,
how
I
fast it
haven't
is?
actually. I did fully intend to, because there's no reason this wouldn't work in Rust. And actually, I remember one of the speakers we had the last session actually was talking about the lack of fast float calculations in Rust and how that's a problem. And so I think he'd written his own crate to handle it. So I'd be interested to see how it would compare, because presumably it's not compromising on the accuracy. And if you don't have a compiler flag to allow it to compromise on the accuracy, then it should be slower. And that would be a genuine use case for why you might want to put this code in, if you don't want that, because it could, at least in theory, be faster. Because like I say, it was faster on the standard MSVC compiler as well. I mean, only slightly faster. But if you had so there's, what's the third one? So there's precise, and there's fast, and then there's another one which I think was like fine or something, which is like the very accurate one. And that one would be considerably slower but you would get a better result. So in Rust, I think it would probably err on the side of more accurate, which
Is
would
there
make it
even
slower.
Rust syntax for casting the pointer to a different type and then interpreting it differently?
So although I didn't actually even get to trying it, so I will get back to you on that. But I'm pretty sure you can do
Definitely
it. Yeah.
would be unsafe block, right?
Yeah. Yeah.
Yeah.
Yeah.
Some crates also allow you to embed C++ code into Rust, so you could do that.
Slight cheat.
Great. Thank you very much, Ciara. Thank you very much, Alex, for your time and your effort for those talks. They've been excellent. I'm sure everybody will give you a round of applause if you could hear them. But I'm just going to give you a golf clap with the back of my hand. Great. Well, Ciara, again, would you like to reiterate the book thing again and talk about that very quickly?
Yes, 14th of October, so 2 weeks from now, we're going to start going through it, and yeah, hopefully it'll be a good way of getting kind of a steady motion through the book and getting that progress, because we get people who've come from C++ backgrounds and some who've done more Rust, but it's very easy to, as well, to fall off the wagon of the book when you start being able to write something vaguely interesting. So it'll be a good way to, yeah, have those study sessions and swap notes on the more subtle parts of it.
Okay, great. And are we going to be trying to do these meetups more regularly as well, Ciara?
Yeah. So as well as having those study sessions in between, so hopefully we'll do the study sessions every 2 weeks, and then that would make our meetups then be on the 6th week. So you would go study talks, study talks is the current planned format, provided we can get sufficient speakers. If anyone wants to do a talk, then please do get in touch, because appreciate that it can be a bit intimidating. As someone who's just done a talk, was quite intimidated, but it's yeah, all are welcome. Any topic, to be honest, that you'll be surprised what people are interested in. I would happily watch the talk on most things that people find interesting. So just drop us a message. We've got an email, we've got Twitter, we've got Discord, and there's Meetup itself. So just message via any of those mediums and you will get a response.
Thank you, Ciara, and thank you for everybody coming along tonight. We will hopefully see you all again soon. I believe that concludes this evening's talks, so everybody can leave if they so wish, or if you'd like to continue on conversations with anybody else, I'm sure you're welcome to do so until Ciara closes the Zoom meet, and then everybody's forcefully led out through the doors, pushed out through the doors.
I'll be kind. We can do any chit chat if anyone has any Rust or C++ anecdotes or
I'm gonna have to shoot off, but
Cheers, Alex. Appreciate it. Thank you.
yeah. But you and I can only think about motorbikes being controlled by Rust games now and cameras. So thanks for that, and maybe maybe next time.
You don't
you'll
need
get to see
sleep
that.
tonight.
can you please make it so you have to wear a motorbike helmet while doing it? Because that would be hilarious.
And some knee pads.
I'm just gonna have to leave before this gets too out of hand. Right. Thanks very much, everyone, and yeah, look forward to seeing you again next time.
Thanks again.
Bye.
Bye-bye. Bye-bye, everybody. Bye-bye.
Yeah, I will close out the meeting in that case and see you guys next time.
Cheers, Ciara.
you.
Appreciate it. Thank you.
Thanks, guys. Bye.